The subject of today's webinar is a DVTest method for tap changer analysis. And during this presentation, I'm going to give a brief explanation of what DVTest method is, how it can be used on different types of tap changers, and what types of problems can be detected by observing the tests obtained by DVGraph. I'm also going to explain how the graphs can be used to ascertain that a tap changer has a specific type of problem. My name is Goran and I work as a test engineer at DVPower. And we have another attendee. Just a second. Hello. Hello, welcome to the webinar series. Can you hear me?
Yeah, thank you.
Oh, okay, I'm just getting started, so you haven't really missed anything. And if you have any questions, I will keep everyone unmuted, so you can feel free to ask questions at any time.
Thank you.
First question is, what is DVTest? DVTest or dynamic resistance measurement is a method of testing on-load tap changers or OLTCs, which determines their condition without the need to open up the tap changer compartment and without the need to actually go into the tap changer pieces and internal construction. So the biggest advantage of this method is that it is non-intrusive and that it can be performed together with the DC winding resistance test. And the reason why it can be paired up with the DC winding resistance test is because it is performed in a very similar manner. You can use the DC currents flowing through the tap changer and the winding, and what DVTest is basically a graph of these currents during the tap changer operation. This test is recognized by some of the world's largest tap changer manufacturers, such as Reinhausen and ABB, and it is gaining more and more acceptance among users and owners of tap changers worldwide. So the graph that you are getting from the DVTest is in fact your results. It is in fact the value that you're getting and which you are using to ascertain whether your tap changer is in good condition. And this graph is recorded for the entirety of tap changer operation for all three phases. And this way you can get the best possible result and best way to detect if any tap changer problems are present. Together with the graph shown in blue, you can also record the motor currents of the tap changer, which is shown in green in the lower graph on the lower part of the screen. And this motor current graph can be used to determine if there is some sort of problem with tap changer motor or with tap changer mechanism, because any sort of obstruction or mechanical problem during the tap changer operation will cause the motor to use more force in order to operate the tap changer. Now, the graph, when you zoom in on it and when you analyze an individual transition from one position to another, can have different specific shapes. And this shape of the graph is different depending on the type of tap changer that you are testing on. For example, here I will focus on Reinhausen type M tap changer, which is very common type worldwide, and which operates using two transition resistors as a temporary carriers of the loads while it is going from position A to position B. What happens during the tap changer operation is that as it goes from A to B, first you have a portion where one resistor is picking up the loads, then when two resistors are connected in parallel, then when the second resistor is picking up the load, and finally when the operation is finished. Now, all these stages of the tap changer operation can be found on the DVTest graph. When you look at the zoomed in part of the graph, you can see that it is on y-axis current, and on x-axis it is time. And on the first part of the graph, you can see that the current is a flat line. The reason for that is because before the point marked with 1, nothing really happens with the tap changer. And no motion is present, there is no change in total resistance in the circuit, and for that reason, the current is simply a flat line. However, when the first transition resistor comes into the circuit, you can see that the current suddenly and sharply drops. The reason for this drop is caused by the increase of total resistance in the circuit between the two terminals to which we are connected. So any increase in the resistance will cause a decrease in the test currents. Then when a point marked with 2, the total resistance decreases because you have two resistors connected in parallel. And then the slope changes again when the second resistor kicks in. And finally, the point at which your transition is finished is marked with 4. And due to the transformer inductance, this current does not immediately recover, and instead it slowly changes itself towards the stationary value. Now, this is just one type of graph that you can see. Basically, every single type of tap changer has its own specific type of graph, depending on the internal construction, depending on the duration of transition, depending on the number of transition resistors which are used, or even if, in some cases, reactors are used instead of resistors. Also, the same type of tap changer can have a different shape when connected to a differently sized transformer, because this transformer has different inductance. For this reason, only graphs obtained on the same transformer are directly comparable with each other. However, some things such as transition time are the same for should be the same for all tap changers in a certain model produced by the certain manufacturer. One other thing that you can see on the graph is called a transition ripple. This is the percentage value that the current drops from its starting value up to the lowest point where the value reaches this point. So this is called the transition ripple. This current is recorded at a very fast sampling rate. And the reason because this is done is due to the very fast transition process. So this entire transition on tap changer type M from Reinhausen happens in 30 to 40 milliseconds. And for that reason, the DV power instruments record the current at every 0.1 milliseconds. And this very high recording rate is important in order to enable capturing all these individual parts of the process and for precise measurements of the transition time of the tap changer operation. So one frequent question is why should DVTest be performed? Why should this extra test be done on a tap changer when there are already other methods available, such as winding resistance test or DGA analysis? Well, I will give you 4 reasons why DVTest is recommended to be performed. The first of these reasons is that tap changers, as the only moving part in a transformer, are one of the most frequent causes of transformer faults. According to one statistic, this tap changer can cause up to 40% of total transformer problems. And for this reason, a lot of tap changer failures happen, and a lot of maintenance work normally needs to be performed. Now, if something happens with your on-load tap changer, in about 5% of cases, it can lead to the failure of the entire transformer main tank. And this is a very major problem, which can cause the entire transformer to become faulty and to need to be replaced. You can say, okay, tap changer manufacturer has its own recommended period of maintenance, so I can just do a regular maintenance according to the number of recommendations that the manufacturer specifies. However, one study shows that up to 12% of tap changers require maintenance before the manufacturer's suggested period. This is the case where, for example, the manufacturer says that your tap changer is good for 30,000 operations, but it develops a fault even at 20 or 25,000, because this sort of problem can never be perfectly predicted. And finally, when you are taking the transformer apart, when you are looking and disassembling the tap changer and cleaning and doing various maintenance works, sometimes it is very easy to make a mistake when you are putting the tap changer back together. For this reason, it is recommended that after you finish maintenance and reassembly, that the tap changer is inspected using a non-intrusive method such as DVTest in order to make sure that the tap changer can be safely put back into service. And I'm just going to make a short pause here, and I'll be back in 10 seconds. Okay, we are back in the presentation, and I will continue with the webinar. So, your next question is probably how the DVTest graphs should be interpreted. So, every type of tap changer belongs to a series of models. And every series of models uses its own operating principle, which provides a different type of graph and requires a different analysis technique. So what sort of information should the operator performing the test know in order to analyze the results properly? Well, they need to know first what are they exactly testing. They need to know whether their tap changer uses resistors or reactors to perform the transition. They need to know the exact model of the tap changer because it helps us compare with our database, and the type of transformer regulation. It also needs to know whether the current is interrupted by vacuum or by oil, and also whether the tap changer is directly connected to the transformer winding, or if it is connected through a series transformer. And this is something that I will explain in more detail later on. Now, the indicators of a problem with a DVTest graph can be various. First among them is the overall graph shape of the DVTest. So what I'm mentioning here is that when you go from position 1 to position 17 or 21 or 33 or however many positions you have, you want your overall graph to be linear. You want the graph to be as smooth as possible in order because that shows you that the tap changer is operating properly. And on this graph that you see on this slide, you can see 4 parts marked in red or marked in green. And these parts correspond to specific points in the tap changer operation where the tap changer uses the same contacts twice. So here it happens on position 2, and here it happens again on the second position past the neutral point. And again you have 2 symmetrical places where the problem happens marked in green. So this tells you immediately, without the need for any further analysis, that a contact problem is visible on 2 specific points in the tap changer mechanism. You can also look at the graph shape to look if the same type of abnormality is present at all even or on all odd tap positions. And this can indicate a problem with the tap changer diverter compartments. Here you can see a graph going zigzag, 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 and this tells you that one of the contacts of the diverter switch has an increased contact resistance. Because in some cases it requires more current, in some cases it requires less current, and since the same contact of the diverter compartments is in the circuit in both cases, this means that your problem is probably located on that side of the diverter. So when you actually look at the diverter compartments, you can see male and female diverter coupling contacts, and if one of them is damaged or burned, you can actually see that as caused by the increased contact resistance. So when this same diverter switch was taken apart and cleaned and the faulty contacts replaced, the same test was repeated after service, and you can immediately see the difference. Because the problems with the contact resistance have been cleared off, you can see a much better and much smoother linearity in the after-service graph. You can also look at the static part of the DVTest in order to make sure that you don't have any problems in places where you would expect that the graph is completely smooth and completely flat. What I'm talking about is this portion of the graph where you don't really expect to see any roughness or any problems with the contacts. So you see on one position that the line is smooth, and on second position it is smooth. But here you see that the moving hand of the tap changer selector has encountered some sort of problem. Now this problem can be caused by contact bouncing over rough or uneven surface, or it can be caused by maybe some burned or damaged part of the stationary plate, which requires replacement or even simple cleaning. And this is very easy to spot and very visible to determine where exactly this problem is located. so that when the tap changer is taken apart and serviced, the one doing the service and the maintenance now knows exactly on which point he should focus himself on. So what this would actually look like on a real tap changer is something like this. You have the moving part which goes from stationary contact to stationary contact, and if it encounters a burned and coaked surface such as this one, instead of sliding over smoothly, you will see a roughness on the graph such as the one we saw on the previous slide. Sometimes the moving arm itself can have a problem. It is not the problem located on the stationary part of the graph. It can be this moving part of the tap changer which develops an issue. And in that case, you will see a bad shape of the graph on every single tap position and on every single operation of the moving arm. And something like this is easily visible when you look at the overall shape of the DVTest graph. So here's an example where erosion of tap changer contact can be seen. And sometimes when the sliding contact has problems, the graph looks something like this because it is encountering arcing, which is causing the entire graph to become very, very strange looking. So this can be seen on this sliding here. And how it looks like in real life is that as this sliding contact became completely worn out, as it operates from one position to the other, it has various types of problems, and all this roughness and bad sliding and bad contact, they all cause the currents of the test to oscillate and to have a strange graph shape. Now, when you zoom in on individual transition, when you go further in on the details of the graph, you can detect additional issues with the tap changer. These issues include transition times, because anytime your tap changer slows down and you don't know the reason why, it can indicate a potential problem. So here you have a difference between operation on even and odd tap changer positions, so that the odd transitions are significantly longer, for example, 112 milliseconds compared to the even ones. And this can indicate that either the spring operating the tap changer has lost some of its power, or that there is some other type of mechanical problem which is causing this to slow down. What it means in real terms for the operator of the tap changer is that every extra millisecond that resistors spend in the circuit, they are exposed to more heat. And more heat means that more gases can become produced in the oil compartment, and that the parts itself have more risk of aging and more risk of damage. So you want the transition time on every tap changer to be as short as possible. And finally, you can look at abnormalities visible in individual zoomed-in tap position, either on individual ones or every second one or contact bouncing, and it can look a little like this. This zooming in is very useful to detect various types of problems because you can see issues such as shorting out of one transition resistor, or one resistor being completely open and opening the circuit down to zero. So all of these issues can be easily seen when you focus individually on the graph. Then you can look at the ripples. and the percentage value that the current is dropping during the tap changer operation. The ripples themselves should follow a certain linear following. So all of these ripples should be roughly even between each other. So if you look at this graph, you can draw practically one line between the first position and the neutral, and a second line between neutral and the last position. However, when the tap changer has some sort of a problem, you can see that the ripples no longer have that smooth linearity. If we look at the same graph where the certain stationary contacts have problems, you can see that the ripples in those positions go much deeper. And the reason for that is the increased resistance in the circuit during the operation. And any increase in the operation on the resistance during the transition will cause the current to drop down more, and in other terms will cause the ripple to become more pronounced. So you can easily see this irregularity on the graph itself. And if you have a 100% ripple or something close to it, this means that one of the biggest problems in the tap changer operation may be present. Here you have an example of a complete open circuit where the current drops from a 20 amp value to 0 during the operation. This means that the tap changer does not make properly, and that instead of making the proper connection to the next point, it just remains either completely open or completely arcing. And this can be one of the biggest problems present on a tap changer, and it can lead easily to the total failure of the main transformer tank. With our TWA40D device, you can perform a DVTest simultaneously at all three phases. The additional information you can obtain from this test is whether your three phases are synchronized or not. And the analysis of three-phase synchronization and various synchronization problems are very easy to spot, because when you zoom in on this simultaneously recorded three-phase graph, you can immediately see that something is off. And this problem is caused by phase C, or yellow phase in this case, operating by 100 milliseconds faster than phases A and B. So here you can see that since the three phases are connected in parallel, and since they are supplied from the same current source, when one phase operates faster than the other two, it causes the other two phases to shortly have an increase of current. And then when it continues to operate and when they also commit their own transition, you see a decrease of current in here. So on a larger graph, this would be a very easy problem to spot. So here is a comparison between perfectly synchronized and a desynchronized graph. And a perfectly synchronized graph is normally the basic rule, because normally the tap changer is operated by the common mechanism, which operates all three phases at the same time. So the only times when you would see any visible desynchronization is when one phase has some sort of mechanical obstruction or something blocking its operation, which causes it to operate more slowly than the other two phases. The second biggest problem of desynchronization is when you have very, very large transformers or sets of three single-phase transformers connected in one three-phase system, which are operated by different control mechanisms and by different tap changers. So this can indicate that the three single-phase transformers are not in sync with each other, and that the control linkage between the three needs to be readjusted. Now, by looking at the second graph that you saw at the beginning of the presentation, the graph of tap changer motor current, you can also perform analysis and see various problems with tap changer mechanism and tap changer motor. So, when you look at the graph itself, you can look at the duration and you can look at the magnitude of the motor current. And you can see if one of the operations is shorter or more pronounced or faster than it should be, and if it operates more or less on individual tap positions. So here you can see that in position 1, the tap changer motor operates for only 2.5 seconds, while on all other positions it operates for 5.5 seconds. And you can also look at the abnormalities of the tap changer motor current shape. So when you compare the first, second, and the third one, you can see that they are not exactly the same. Because on the second one, as the tap changer operates and moves the spring towards the point where it actually moves the positions, you can see that this force is not applied equally, but that it increases as the tap changer operates. And this increase in force is visible as the increase of tap changer motor current recorded by the instruments. Now, here is an example where a lot of different problems from the DVTest and a lot of different tap changer issues can be simulated and shown on the graphs in order to determine what exactly type of problem is visible and present on a tap changer. Here is a case where a test was performed on an old out-of-service transformer which had an open tap changer compartment on which different issues and different problems could be simulated. So we created a reference graph, then we introduced one problem, recorded a tap changer graph, introduced second problem, recorded tap changer graph, and this way we gain a lot of valuable knowledge in order to see what sort of problems can be detected with this method. So here is how this transformer looked like. It was out of tank with easily accessible windings, and the tap changer compartment and all its connections clearly visible and within reach. So the first measurement which was performed was done without making any simulated errors and without introducing any types of problems on the tap changer. This is also an important step because you need to have a reference in order to have something to compare to when you actually detect a problem. So even if your transformer does not have any sort of problems, the graph that you recorded on it is still valuable, because later when you do have problems, they will be more easily spotted by comparing it to the graph you recorded back when it was in good operational condition. The first problem which was introduced was a problem with moving selector contact. This is the moving selector contact which slides between the different positions of the selector as the tap changer operates. And this spring which holds these two arms together was completely loosened up. So now when the tap changer was going from position 1 to 2 to 3, etc., you could see that it vibrates. And every vibration of the moving selector contacts causes the current graph recording to become shaky and to become uneven. So when you compare the reference graph to the recently recorded graph, you can easily see the difference. And this is a real problem which can be easily present on actual tap changers, because you don't really know how tightly those bolts are actually bolted down. Now, the next step was fixing this problem, and now one of the bolts on the stationary contact was again weakened. And by operating the tap changer from first to the last tap position, you can immediately spot the exact location where the faulty contact is present. Because of the increased vibration and because of the worse operation of the tap changer, you can see that the faulty contact has smaller currents, or in other words, higher resistance, and much more pronounced vibrations when compared to the other tap positions. And finally, one additional simulated fault is represented by the duct tape placed in the path of the moving selector contact. So this duct tape was placed in order to completely interrupt the circuit and to see what would happen in that case. And as expected, the first couple of times an open circuit was detected and an error was diagnosed by the instruments. However, since we used 20 amps for this test, eventually the currents managed to burn through the insulation and to establish a path for the currents. So this is a major advantage of high test currents used in this type of test. When you're using very low currents, such as half an ampere or 1 amp or 2 amps, sometimes you can have a false alarm where the problem is recorded because some oil film is present on the surface of the contacts. This does not happen when you use high test currents, because any obstructions which can be easily cleaned and which can be easily wiped during tap changer operation will be pierced by the high currents used for the test. So you can see how the graph looks like and how a problem is clearly visible. You have normal ripple on 1 position, 2, 3 positions, and then when it encounters the obstruction, you see the current drop almost down to 0. And then the second time the obstruction is encountered, you can see that the resistance is a little bit less, so that the current now drops to 4 amps instead of 1 amp as in previous case. And by the time the fourth operation is done, you can see that the current drops down to 6 amps. So you are measuring 4 different ripples in 4 cases where the transition resistance is in the circuit during the operation is different. So as I said, the goal of this webinar was not to go into detailed analysis of various types of problems and various issues that can happen on a tap changer. The goal of the webinar was to present to you what the DVTest method is and what types of problems can be detected. So this is a reliable, non-intrusive method which has a very high repeatability of results and which provides a very powerful way of detecting tap changer problems even in their earliest stages. Dynamic resistance measurement is also used on circuit breakers where it is used specifically to test the condition of the arcing contacts of a circuit breaker, and it is getting widely accepted as well on on-load tap changers. An additional advantage is that this method enables testing of any on-load tap changer type, whether it is oil or vacuum, whether it is reactance type or a resistive type. And the best way to compare the results is by either comparing the 3 phases with each other or by comparing with the previous reference measurements performed on the same tap changer. Now, one thing that I would like to mention is that this test is not all-powerful. If you use DVTest, it doesn't mean that it replaces all other tests. However, what it does do is that it provides a very powerful tool, and it provides an additional tool for the engineer who wants to ascertain his tap changer condition. So the DVTest findings can be confirmed and supported by other tests, such as measurement of tap changer motor currents, measurement of winding resistance in various stationary contact positions of the tap changer, and also by dissolved gas analysis.